Okay, going over the exam here. So with the first one, if you were to count these lines, 1, 2, 3, 4, 5, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then you would be led to 60 degrees. However, there's a warning here to look for another solution because you want the smallest angle. And due to the symmetry, it's better to look at something a little bit off axis, not, so that you can count like these gumdrops would be better. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that would give you 360 over 12. That would give you a 30 degrees. And the problem says you go with the smallest one. The symmetry is so beautiful in kaleidoscopes, it's so easy to count a pair as one. So if you counted these as 1, 2, 3, 4, 5, 6, you would get the wrong answer, 60. So you want to go with counting these oddball things, 1, 2. I would stay away from the edges because some things go off the page. Don't even look at that. Stick with stuff that you can see. All right, for the polarizer one, the main thing here is you have a vertical polarization and a horizontal. Nothing can get through because these are crisscrossed. So that means anything that has a V and an H, you can't have, or H and a V. So you can't V and H. This one, V and H. So this one is the only one that doesn't. So this one here, when you go V slant, some slips through because it's not crisscross, and then some can slip through there. So the main thing here is you look for VH and HV, and they're the ones that get killed. Unpolarized light comes in, and you have a filter, a polarizer coming in, and you can think of all kinds of directions. And this is going to let all the, let's say this is oriented vertically. That lets all the projections vertically come in, and that will be half the light. So you'll get 500 coming through there. And then if the second polarizer here is oriented with some angle, say 45 degrees, then you could use the Malice's law, but actually you can use logic here. Some's going to get through because this is a vertical and this is a slant. So that means you can't have 0. You can't have 1,000 because you have a filter there. You can't have 750 because 500 goes by. You can't have 500 because you have another filter. It's got to be this one. So you don't even have to do anything more. The Malice's law could be used as a 45-degree angle, and the cosine squared of 45 is going to get you as, this is the square root of 2 over 2 squared. This is a half. So that means a half of the 500 it goes through, but you don't need that. You can get this one by logic based on the choices. For an electron to give off electromagnetic radiation, you need acceleration. So you look for acceleration. Here's acceleration, 3. And if you go in a circle, that's acceleration because you have v squared over r is your acceleration in a circle. So this has to be the ones that have acceleration would be here 3 and 4. Okay, for this one here, you want the divergence. So the divergence is you basically here are going to have an I hat and then a derivative with respect to x and a j hat, a derivative with respect to y. And really there's no z's here, so I don't even worry about anything else. So when this comes in and hits this I dot I, you're basically taking derivative of x with respect to x, that's a 1. And then the i's go away, and this would be plus 1. This is a 2. So if you do this next one, and I'll just go ahead and write this next one out. dx, dot, I, it's going to be dot. These things, when you do the divergence, you have del dot, so you're working on a vector. So this would be I hat here, and then plus j hat, d minus y, dy. This is a minus y and a j hat. So you're going to get a -1 from this thing. J dot j is a 1. you're gonna get a plus 1 from here, so you're gonna get 0. So this is the one here. You can stop. Yeah, this is no way. You're just gonna get here 2x y. Here you're gonna get minus the sine of x plus minus the sine of y. Here you're going to get e to the x minus e to the y, but you don't need to do all that. You'll be wasting time. As soon as you get the answer here, like, you're finished. So if you look at the one with the white light across the room and you want to know what you're going to see here, the key idea here, the basic idea with diffraction is if your wavelength, see, is real tiny like this, then the opening looks really big and you get less diffraction. So that means you're going to have less diffraction for the short wavelengths, which would be blue. If you've ever looked through a diffraction gradient and see this, you will see the blue ones are closest to the center. See, blue closest to the center. Everywhere blue is closest to the center, less diffract, and reds are farther away. And this next one wants to give a rating for resolution. And for the resolution on this one, you have to have a high rating if the delta lambda is small. That's what it basically says here. A high resolution means you can distinguish things close together. This is no way. That's going to be if you have a small delta lambda, this is going to be a small rating. You don't want that. You want to have a big rating. So you don't want these. That doesn't work. And this is the only one that has a good rating for a small delta lambda. So that means your resolution is good if you can resolve lines that are very close to each other. So this is it. This one, no, you have to have the one where a delta lambda, when this is small, you get big, you get a large rating. So this is the one, and this is good for 2 reasons extra. This is what they use because it's dimensionless. That's nice, and also it compares it with the wavelength. See, if this wavelength is very, very big, like say 1,000 nanometers, and you're still resolving 1 nanometer, oh, that's more impressive than if you had 100 nanometers and you were doing 1 nanometer resolution. Because see, this is a long wavelength here, so that is even better rating. Because you wouldn't expect this much. You might say, if the wavelength is so big, well, it will give you a break. I mean, you have to resolve as much, but no, you're still resolving more. Okay, for this one here, let's say you want to know when n is large. Okay, when n is large, we then plug in. So what is the n times alpha? N times alpha would be here 5 pi over 2. All right. So that means this thing becomes the sine of 5 pi over 2 divided by, and it's going to be squared, divided by n times the sine of the alpha, which is the same, the alpha to put the whole thing in like this. So if the numerator here, when you have the sine, if you're at pi over 2, or if you're at 3 pi over 2 or 5 pi over 2, that's going to be 1. So the numerator is a 1, and the denominator, since the n is very, very big, this is very, very small, so you could then use our approximation where sine of theta is theta, and you get this. The n's are going to cancel. The 2 will flip, so it'll be 2 on top, 5 pi on the bottom. That's this one here, 2 on top, 5 pi on the bottom, and you got the squared going on there. For this one here, the irradiance, you want EP and EP star, complex conjugate, so that's E naught squared, 1 plus I, 1 minus I, and this is 1 plus 1, and we have to also have the 1/2. So we have to have the 1/2, can't forget that. That's your irradiance formula. So that means that E naught squared over 2 times 2, and that means it'll be the E naught squared. Yeah, remember that 1/2, that's tricky when you have the irradiance. Okay, now we're ready for one more. The irradiance, if you block all the Fresnel zones except the first one, then that's a certain value. Okay, we got that. And it says it's greater than 0 because you have to be careful. It depends on where you are along the axis. central axis from the zones. So if you're at a certain point here, you're seeing something, I1 greater than 0, then if you now block all the zones except the first two, that second one is going to work against you. So that's going to decrease. That's what's going to happen there. This is our first problem. And what we need to have is, we need to have this RP, this one has to be 0. Okay, so if RP is 0, that means, well, first of all, we can clean up. It says here the N2 is N. So let's go ahead and clean up. So RP is N times cosine theta 1 minus cosine theta 2 over, actually I really don't care what's down here, and if it's an exam and my time's valuable, I might just say, look, I just need the top to be 0, because see, this is not going to be 0 down here, so that means N cosine theta 1 is cosine theta 2. Then if I go over to here, I can replace this and this equation here, and this one I will write out with substituting the 1 for the 1 for the N1, and here minus N cosine theta 2, and this is then cosine theta 1 plus N cosine theta 2. Here, let's go ahead and, you would be doing this on a piece of paper, not in the margin, so let me go ahead and write this out again so it's clear, everyone sees what I'm doing. All right, minus N cosine theta 2 over cosine theta 1 plus N cosine theta 2. Okay, I like it without those subscripts, and since they gave them to me, this looks nice. So now I'm going to replace this theta, this one here can be replaced by N cosine theta 1. So I can do that in two places. So then I'll have RS is cosine theta 1 minus N squared cosine theta 1 over cosine theta 1 plus N squared cosine theta 1 by doing the substitutions. And see, all the cosines cancel now. I get 1 minus N squared and 1 plus N squared. And I want for the big R is I got to square this coefficient, or you do this complex conjugate, but there is no i's, so that's good. So I'm going to write this as here. Just my preference is to write the N first. So since we're squaring, it doesn't matter which one we can do. So we're doing this and we're squaring it. So that is the answer. All right. Now for part B, it says if N is exactly 3/2, what's the answer? Well, that would be then here 3/2 squared minus 1 over 3/2 squared plus 1. Whole thing's got to be squared. All right. So this is for N equal 3/2, special case. So this would be 9/4 minus 1 over 9/4 plus 1 squared. And this would be here 9/4 minus 1 would be 1 is 4/4, so this is 5/4. And then if you have 4/4 and 9/4, that's going to be 13/4 squared. 4's go away, and you have 5 over 13 squared. So the RS in this particular case is 25 over 169. So you want to box that off. It's dimensionless, the reflectance. And then for the last part, it wants to know the 3 significant figures. It wants to know the 3 significant figures. So now you whip out your calculator. And when you whip out your calculator, you would get here 0.148. Okay, and that's it. Okay, now we go to the Fourier series question. Here's Fourier series, and we want to, for part A, this is an upside down parabola. Go ahead and match it. So you have f of x is ax squared plus bx plus c. And if you put in f of 0, you got to get pi. Because at f is 0, you got pi. So that means c has to be pi, because when you put in 0, x is 0, that's going to just get you c. And then here, if you put in plus or minus pi, you have to get 0. So that means here for our next step, but before I do that, I notice this is a symmetric function. If this is a symmetric function, this is gone, because that's an odd function. See, x is positive on one side, be negative on the other side, so it'd be an upside down part of the graph on that side. But since if you have an x, you have the same value here. If it's a minus x, plus or minus x give the same value, the same function, f of x. You can't have the b. So that means here, I have so far f of x is ax squared plus pi. So when I set this equal to 0, when I put in here plus or minus pi for the x, I'm just going to put in a plus pi. I'm going for the one on the right. Plus pi, it has to be squared. And then I add the c, that has to be 0. So that means a times pi plus 1 equals 0, or a is negative 1 over pi. Okay, so that means I have my function. I have a is negative 1 over pi, I have b is 0, and I have c is pi. So it would be nice to, we determine them. So in other words, a equals here negative 1 over pi, b equals 0, and c equals pi. Okay, then it wants to know that for the next step, part b, which Fourier coefficients are 0? Well, since this is an even function, that means all the b's are going to be 0. The b's are gone. All right, so that answers that question. And then the last question says just do the constant. In other words, the first constant. I mean, these are all constants, the a's and the b's, but it says just do this, just do the one, the a naught is what we're doing. And they gave us the formula. See, here is the formula. So they gave us the formula. And here, since this is an even function, I can integrate, put a 2, and integrate from 0 to pi, since it's an even function. And my f of x is minus x squared over pi plus pi, just copying down from what I had earlier. You know, the a is negative 1 over pi, and the b is 0, and the c is pi. So integrating this, minus 1 over pi, well, this is going to be fairly easy to do. These are friendly. So this is x cubed over 3 plus pi x. We have a 2 over pi out in front, and we're going to go from 0 to pi. That makes it easier because the zeros, there's going to be nothing in the lower limit, just the top one. So this would be 2 over pi, and you would have here, this is a pi cubed over that, so it's a minus pi. It's going to be pi squared over 3 plus pi squared. All right, so let's go ahead and finish this. So this is 2 over pi. I'm just going to copy this again and pull that pi squared out. So this is minus a third plus 1. Pull that pi squared out. So it looks like in here we have 2/3. So we have 2 pi, since 1 pi will cancel, and this is going to be 2/3. So it looks like we have 4 pi over 3. So a naught is 4 pi over 3. That takes care of it. We got it. So now we move on to question 3. Okay, and what we want to do here, we got some equations given to us, and what we're doing here is we have x's labeled for us. We have the first minimum, we have the first maximum, this is the central maximum, and then we have the second minimum, and then we have the second maximum, and we have then the next minimum, the third minimum. Now the question is asking us to fill out a little table. And it's basically saying we just want what's labeled x1 and x2. That's all you have to do. You don't have to do these others. All right. So if that's the case, we want this one, x1 and x2. Now x1 I can get easily because I know that the beta has to be pi. This next one's trickier because, see, beta here is 2 pi for the next one, because you're looking at the sine. You're looking at the sine square root of beta. So where do you get your zeros? Remember, when your beta is 0, you get the L'Hopital's rule, you have the maximum, the central maximum. So your zeros are going to be, when the sine is 0, it's going to be pi, 2 pi, 3 pi, etc. So here, this first one is going to be at pi for beta, and then this one at 2 pi. I don't know what this one is because of this weird stuff in the denominator. It's going to mess me up. But it says you can take the maximum, even though they're not quite in the middle. It says you may take them to be exactly in the middle. Well, that's nice, because that's what they're telling me to do now. I can take this beta here, has to be then 3/2 pi. Now, if I got pi and then 2 pi, 1.5 is in the middle. So this is saying I can take that to be exactly in the middle. Okay, now that being done, I'm ready to go. I can now do all of them. I'm going to do the minimum first. So for the minimum, it's easy for the minimum to fill in the I, because the I for the minimum is going to be 0. It's like it's killed. So I can put this one down, the irradiance there. I can just see it's 0, and it's going to be 0. It's a minimum, so I don't have to figure anything out. Just put 0 there. And then now let's do what the x is. What is this x? Well, remember the x here, if you take the x and compare your x with your L, you have, this is the usual approximation we make, that tangent of theta is, x over L, but that's approximately the sine of theta, since the angles are very, very small. So we can use that same approximation. All right, but I need to work with beta first. Beta is equal to pi. Now this equation, I'd rather get rid of this k, 2 pi over lambda. If we do that simplification, we're going to get here beta is equal to pi over lambda d sine of theta. Now that's important to do because, see, I need that sine theta. That sine theta is going to be handy. So now once when I get this, I notice that they're giving me d as 160 lambda. Well, I'm going to take advantage of that and go ahead and use that. So if we do that, then the beta is going to be 160 pi times sine of theta. All right, that's going to be my favorite formula there. So then if I want to do that for the beta's pi, so that's the first case, and I'm going to say this is the first kx1, so beta 1, I'm going to make that a pi. That's 160 pi times sine of theta. So that means with these pi's, going to cancel off here. That's probably a little sloppy. You shouldn't do that. Probably should write that again as 1 equals 160 sine of theta. And I'll put a 1 there. Then that means sine of theta 1 is 1 over 160. And that is, remember my formula, this is x over L. But they said L was 1 meter. So if L is 1 meter, then I just want 1 meter divided by 160. We do that division, we're going to get here with the calculator 0.0063 meters. Move the decimal point over 3, that's 6.3 millimeters. And this did ask for millimeters, and it also asked for to do 2 significant figures. So that means we put in this little place here, 6.3. Okay, then we go on to the next one. Here, we're going to use the 3/2 pi. So that means the beta 2 is 3 pi over 2. And then I use my master formula, which is 160 pi sine of theta. And that's the second theta. All right, just using my formula from before, this 160 pi sine theta. So then now we really should write it again. It's not good to start crossing things out like that, especially when you have that beta there. That's not good. So let's go ahead and say 3/2 is 160 sine theta 2, and that means sine theta 2 would be 3 over 160 times 2, which is 320. All right. So with that, we can then use the calculator and get 0.0094 meters, and that's going to be 9.4 millimeters. 9.4 millimeters, because this is meters. So I come over to here and I put 9.4 in the box. And the last thing to do is to find the irradiance. But the irradiance formula we have given up here. So go ahead and write that down again. It's the sine squared beta over beta. And I know what the beta is. It's a beta squared rather. And I know what the beta is. The beta is, for this case, this second case, is 3/2 pi. So that means I need sine 3/2 pi over 3/2 pi and square this. But see, the sine is 1 there. And then this is going to be 9/4 pi squared, which is going to flip to 4 over 9 pi squared. So 4 over 9 pi squared, I mean, it's basically the 2 over 3 pi, squared, if you worked on the inside there. So you can just do this on a calculator first if you want, and then square it, or you can just work with that. But in any case, you're going to get 0.0450, and that's it. That's what we want. This is the relative irradiance. I'm going to put down divided by I naught like that, because that's the formula that was given to me here. If I have, the relative radius, keep the notation precise. This is the relative irradiance is what this is, I over I naught. So it's just the sine squared beta over beta squared. So here I put 0.045 and I got it. Okay, the last one here, P4. Okay, if we go to the last problem, this one wants to know what the irradiance is, the first maximum. All right, the first maximum to the right of the central maximum is this one here, and it's slightly to the left of this one here, the m equal 1 case. All right, it's telling me that, but it says neglect that slight difference. Well, if I neglect that slight difference, I know that this light, pink one back here it's saying here that's my interference. So if I go to the interference, that's going to be this part. So when we have 0, say degrees, this is your angle theta. And remember, we have 0 degrees, alpha and beta are 0. So that means this is the central maximum. But if I want the one over here, I want to know where cosine is going to be, maxed out again. Well, the cosine will be maxed out again when you have, the cosine, you want to go to pi. So if you go to pi, then you have, when you square the cosine, it's going to be the same. It's going to get you the 1. So you want the pi. You want alpha. That's the key. You want alpha to be pi, and that's going to unlock the secret to do the problem. So if the alpha is pi, then what we'll do is we'll go to these equations and go ahead and put in our 2 pi over lambda. 2's would cancel. This would be A, this is alpha's A over lambda times the sine of theta. Let's make sure we get this right. This is a pi up here, A times pi. 2 cancels, but you still have that pi there. But the alpha, we already agreed, for this point here has to be a pi for the alpha. So if the alpha is a pi, then what you get here is A over lambda times the sine of theta is equal to 1. Now we also know that it's given that the A is 6 lambda. So if the A is 6 lambda, then you have 6 times the sine of theta is 1, which means the sine of theta is 1 over 6. That is important information because I have to figure out what beta is. So this is what I need here to go up into there. So that means beta here, if I do the same trick with the 1/2 2 pi over lambda b sine of theta, the 2's cancel, and I get pi over lambda b sine theta. That's going to be my beta. And here I know that the b is given as 2 lambda. So if b is 2 lambda, then this is a 2, like this. We're going to put the sine of theta as 1/6, which we already knew. So this beta is pi 2 over 6, which is pi over 3. Okay, so now I'm ready to go because now I'm going to have everything. See, the IR is the cosine squared alpha sine squared beta over beta squared. Since this is 1, I just need to deal with this. And this is going to be the sine of, I'll put the square on the outside, pi over 3 over pi over 3. The denominator will flip. I'll get 9 over pi squared. And then I'll have here the sine of 60 degrees squared. And the sine of 60, if you recall, this is the 1/2, and this is the square root of 3 over 2. So that would be 9 over pi squared, square root of 3 over 2 squared. So that's 9 over pi squared. This is 3 over 4. All right. And that means we're talking here for the irradiance, we're talking 27 over 4 pi squared. That's it. And it wants to know as thick in figures, like, what's it say? I think it's a 3, wants 3. So if you then divide this out with the calculator, you get 0.684. That's it.